Okay, so the CANFD being compatible with CAN 2.0 setting. So on this side it's a STM G431 controller, and on that one it's a STM F446. And like with the nuclear board, I'm using a CAN transceiver, like it's the SN65HVD230, which is a CAN 2.0 standard, so it only supports up to like 1 megabits per second CAN transmission. Yeah, so on the software side, we need to configure, so firstly the CAN 2.0 side. Yeah, so in the connected, first of all, like because these two are all like 4 series chips, so I'm running both of them at 160 megahertz core clock. Yeah, and for the CAN peripheral configuration, I forgot where the CAN is located in the clock tree, but like with a prescaler of 8, we get like 200 nanoseconds for one-time quantum, which is like the basic time unit for the CAN protocol. Yeah, so yeah, that's it. And then we need to configure like how many time quanta in one CAN bit. So with some posts I read that like the optimum ratio is like the first time segment or the first bit segment in the total should account for like about 87.5%. And here we're using a ratio of 3:1, so that's like 75%, which is pretty close to that optimum setting. So yeah, so like this works. And then we get time for one bit is 1000 nanoseconds, and thus the baud rate is 1 megabits per second. The resync jump width, the default is 1 time, and from some Stack Overflow posts I read that like with a higher resync jump width, the CAN bus will be more reliable. So like currently I'm using a pretty short CAN bus distance. So if with longer CAN bus it become unstable, we can try to increase this field. Yeah, so this is the CAN 2.0 side. It's pretty similar with the CANFD side. So similarly, the core clock is 160 megahertz. And for the CAN peripheral, I'm not sure about the top, like the basic parameters. So I'm keeping it as default with the frame format is classic mode, which is the one compatible with like classic CAN. And I'm keeping all these the same. I think this is for configuration where like for CANFD you can have different baud rates for the like the arbitration field and also the data field. But like for CAN 2.0 they are the same, so we don't need to configure any of these. I will use the configuration down here. So prescaler, this is 16 because like the 2.0 one is 8, and that's because like for the 2.1 side I can set the second time segment to 1, but here actually the minimum value is 2. So because of that we need to scale the entire like time quantum by half, like shorter them by half, so that we have 16 as a prescaler, 100 nanosecond per time quantum, and then a 7:2 ratio, which results in Yeah, I think it's time segment 1 plus time segment 2 plus 1. So that's 10. And then there's a 1000 nanosecond for 1 bit and like 1 megabits per second frame. And this is like also pretty close to the optimum sample point. So yeah. And then these two can actually communicate with each other. And that's the like kind of like peripheral setting part. And then I've tried to implement the CAN protocol, like the motor controller protocol, because like for standard CAN frame, it supports like 11-bit CAN ID, which in theory you can hook up that many devices on the CAN bus, but actually we would rather have a small number of devices connected to one bus and also have like a bunch of field to assign like different functionality according to, like corresponding to that device. So like basically what I'm trying to say is like this is the CAN ID and we can divide them into two sections. So one is for labeling the device and the other part is for like within that device we can have different kind of like API indexes to call different functions to that device. And with that we can use the entire 8 like data bytes as the data itself and rather not waste that for indexing. Yeah. And so here we are dividing them as like the first 7 bits are the function ID and the last 4 bits are device ID. And because the CAN bus arbitration, it's most significant bits first, which means we'll put the device function ID in the first part and the device ID as the last part, so that we can assign different, like we can arbitrate based on the function ID first and then device ID. This is useful because, like for example, we have a bunch of motor controllers and we want to e-stop all of them. So the e-stop message will actually override the other type of messages first, and then we arbitrate based on the device ID. Yeah, and yeah, so it arbitrates from the most significant bits first, and thus we want to put the function ID first. And here's the code of it. So starting from so in this setting, this one is the motor controller, and this one is acting like a CAN to serial adapter, and I'm using the host PC Python script to issue the commands to the motor controller and like being able to read something back. So on Python side, we have like the CAN ID is encoded in this form. Like function ID is the more important ones, like the more significant ones, and then comes the device ID. So for example, with a device ID of 2 and function ID of 0, we can trigger the CAN transmission. Yeah, and then we can. Oh, okay, actually it's not capturing. Let's try again. Yeah. So now we can see like in the actual CAN frame, the ID is 2 because like device ID is the non-important one and thus it's like the lowest significant bit. Yeah. And so the lower ones are sending from the SN65 CAN transceiver, and the higher ones are sent from the motor controller, because they are using different CAN transceivers, so they have different voltage levels. But well, it's working, and we can see like so in this protocol, like with the data length of 0, it means that we're requesting the data, and like the target device will respond with the same ID and with actual some length of data as the response message. Yeah, so this is the frame. I'm not sure why it transmits 2 frames, so that might be a bug in my code, but like actually anyway, it's working. Yeah, so just want to document this. And also, while we are here, there are some things to there are some pitfalls that I want to document also. So the CAN peripheral, it requires the CAN RX pin to be put, like electrically being put high when the CAN peripheral initializes. So to do that, either we need to configure the GPIO to make the RX pin internally put up, or we need to hook up a CAN transceiver when the device is initializing, because the CAN transceiver, the hardware will pull the RX pin high. So we need either this or that to be able to initialize the CAN peripheral. Otherwise, this function will return Hall error, and it will print this message. Yeah, just a note. And also, CAN activate notification. This function is basically the enable interrupt of the other peripherals. Yeah.